Hey guys, this is Darshan Lokhande. I am a pre-final year BTech CSE student at IIIT Pune. Welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn data structures and algorithms, this is the one-stop destination for you. We post weekly problem explanations and concept videos. So don't forget to subscribe to our channel by hitting that subscribe button and also the bell icon. The question that we are going to solve today is root the tree. The question appeared in September lunchtime and has a difficulty level of easy medium. The prerequisites for this problem are trees and related properties. Our agenda for today's video is going to be as follows. First, we will walk through the problem statement and try to understand what the problem is trying to say. Then, we will see step-by-step solution and how to approach it, followed by which we will be seeing the pseudocode and then implementing our code in C++. The problem statement states that we are given a directed tree with n vertices and we have to perform some number of operations on the tree such that finally it becomes a rooted directed tree. So there are many terms used in this question. You will find the terminology and all the definitions in the first para of the question. And also in the upcoming slides, we'll be seeing them with the help of diagrams. So the question mentions some terminologies like a directed tree, that is, let's say DT, then a rooted directed tree, let's call it DRT, and also simply just a tree. So all these terminologies you should be familiar with before beginning the question. And also the question states that the operation that we have to perform on the given directed tree is as follows. First, we have to choose some edge in the given graph, then remove this edge and then again add a directed edge such that the tree still remains a directed tree. So this is an example of a directed tree. Why it is a directed tree? Because the structure of the graph looks like a tree and the edges have directions as well. So a directed tree can be simply called as a tree with its edges having directions. So as you can see, if I remove the arrows or the directions from the edges, the figure that I get is equivalent to a tree. But what is the task in our question? So initially we will be given a directed tree and then we have to convert this directed tree into a rooted directed tree. So what do we mean by a rooted directed tree? A rooted directed tree is a tree such that we can choose some vertex, let's say R, that is the root of the tree, and we can visit all other vertices by traversing through some edges. So if I take this example on my left and if I, let's say, choose 8 as my root, I can travel to 4 from 8, I can travel to 7, I can travel to 9, also I can travel to 1 and 2, but I cannot travel to 3, 6 and 5 using the directed edges present in the tree. So although it is a directed tree, it is not rooted, right? So we have to perform minimum number of the operations mentioned in the question such that we are able to convert the directed tree into a rooted directed tree. So in the same example, if I remove this edge and add a new edge from 1 to 6, it is still a directed tree, right? Also, if I remove this edge and add this new edge, and also if I remove this edge and add this new edge, then the figure still remains a directed tree, but now it is also rooted. Why? Because if I draw the final diagram, that is this, so you can see that now I can choose 8 as my root and I can travel to all the other nodes using the directed edges present in the tree. So this is a directed rooted tree. So how many operations did we take here? 3, right? But the question is it the minimum number of operations? We don't know, right? So what is our task? Again, to summarize the question, we will be given a directed tree. There is an operation that we can perform certain number of times including 0, and our task is to perform minimum number of such operations to convert a directed tree into a rooted directed tree. At this point of time, I would like to mention that if you haven't yet tried the question, give it a try and then come back to the video and continue with the editorial. So as we begin the solution to this question, the first common property that is necessary to know here is that for a tree, every vertex except the root has exactly one parent. So if we see a normal tree or undirected tree, it will look something like this, right? So there will be a node called as the root, then there will be some child nodes, then again there will be some child nodes, and so on, right? So we here can see that except the root, like if this is the child node, then this is the parent node. Yes, right? We can see this clearly. But for a directed tree, by definition, we know that if there is a edge from vertex u to vertex v, then u is the parent and v is the child node. So the property is what? For a tree, every vertex except the root has exactly one parent. And we know that this property holds true for normal trees. But I am saying that this property will also hold true for directed rooted trees. That is, all nodes in the directed rooted tree except the root itself will have exactly one parent, that is exactly one incoming edge towards them. So why is this true in the first place? Let's take a counter example. What if a node had two parents in the directed rooted tree? So the condition would look something like this. So let's say there is a child node C and has two parents, namely P1 and P2. So this is how the directed tree would look like. The part of the directed tree would look like. And also the if we remove the directions, the equivalent would look something like this. So there will be a node P1 and there will be a child C and there will be again a node P2. So if this is a directed rooted tree, I am writing here, if this is a directed rooted tree, this is how the tree would look like, right? So as this is a directed rooted tree, of course there will be a root. So as this is a small part of the directed rooted tree, let's assume that the root is somewhere up here. Okay, so now as it is a directed rooted tree, by definition, there must be some path from root to P1, right? So there must be some path from root to P1 and similarly there must be some path from root to P2. So if we draw their equivalent in the normal tree, so the root will be somewhere here and there will be some path from root to P1 and some path from root to P2. But this defies the original definition of the tree because we know that tree is nothing but a graph without a cycle, and here we can clearly see that there is a cycle. So this condition can never occur. Why? Because if a node has two parents, then there is a cycle in the graph and it no more remains a tree. So yeah, our main target in this question is going to be to create a final directed rooted tree such that in degree of all vertices is at most 1, or to be more precise, the in degree of exactly one node, that is my root, is going to be 0 and the in degree of all other vertices should be exactly 1. Right. So first of all, what do I mean by in degree? So let's say there is a vertex X which has 3 edges incoming towards it. So the number of edges incoming towards a vertex is nothing but its in degree. So here, for example, the in degree of X is what? It is 3. So now we know that in degree of any vertex cannot be greater than 1 because then it would not remain a directed rooted tree. But why should the in degree of exactly one node be equal to 0 and that too only root? So to understand this, let's take a quick detour. So it can be proven using the pigeonhole principle that if more than one nodes have in degree equals to 0, then there is at least one other node with its in degree greater than 1. Why? Because the invariant in this question is the summation of in degrees over all the nodes x. Okay. So now our task is simplified even further. We just have to ensure that all nodes except one node have in degree exactly equal to 1. Right. So initially the given graph or the given directed tree will have three sets of vertices. Some will have in degree equals to 0, some set of nodes will have in degree equal to 1, and some set of nodes will have in degree greater than 1. Right? So these nodes, we are not going to touch them. Why? Because they are already perfect. Only thing that we need to ensure is that finally the count of this set is 1 and the count of this set is n minus 1. Right. So if there are, let's say, some x number of nodes over here and some y number of nodes over here, we need to reduce y to 1 and x to 0. So how are we going to do this? We are going to do this by performing the operation stated in the question, and that too minimum number of times. So if this count x, that is the number of nodes initially having in degree greater than 1, is a non-zero number, so we definitely know that then the count y is definitely greater than 1. Why? Again, this can be proven easily using the pigeonhole principle, but this time in reverse, and combining it with the invariant, that is the summation of in degrees over all nodes x in our graph, we can easily prove this fact. So if we have some node with in degree greater than 1, then there are at least two nodes with in degree equals to 0. To see this, let's take a small example. So here you can see that in the small part of the directed tree, I have a node C which is having more than one in degree, right? So the in degree here you can see is 2. So let me write the in degree for each node. So this is a very small example, but it is enough to prove our point that how we are going to perform the operations. So the operation is going to be as follows. As you can see that clearly when one node has in degree more than 1, there are at least two nodes with in degree 0, while the tree being directed and maintaining the structure of a tree as well. So the operation that we are going to do is remove one incoming edge from the node having more in degree. That is, I can erase this edge over here. So now we are left with two components, right? And now to satisfy the in degree of 0 to 1, what I can do is choose one node from one component and connect it to the 0 in degree node from other component. So now you can see that the in degree of this node has become 1, and automatically, as the definition of directed rooted tree we have seen in the beginning, and now as the condition of exactly one node having in degree 0 and all others having in degree 1 is satisfied, we now have a final directed rooted tree with minimum number of operations, that is 1, right? So we saw that to satisfy or convert one 0 degree node to 1 degree node, we require exactly one operations. So we know that initially there are y number of nodes having in degree 0, and at the end we need exactly one node having in degree 0. So what is the total number of operations we require here? Exactly y minus 1. So that is what our answer and our solution is going to be. So when given the initial directed tree, we will count the total number of nodes having in degree equals to 0, and let's say that count is y, and simply our answer is going to be y minus 1. I hope you guys have understood my solution. If you want to master competitive programming while learning from world-class programmers, which include ICPC World Finalists, IOI medalists, and some top-rated programmers from the world, make sure to get our subscription on Unacademy Plus. We have live classes, recorded sessions, practice problems as well as doubt clearance on Unacademy. Also, don't forget to use my referral code DarshanCool25 for instant 10% discount. So now that we have seen and understood the solution, let's get to the pseudocode. So the pseudocode goes as follows. For each test case, first we will take the input for n and then create an array in that stores the in degree for all the n nodes. Further, we will take the info for each edge uv, that is edge going from u to vertex v, and then increment the in degree of v by 1. Once we have taken all input for all such edges, we will count the number of nodes with in degree equals to 0. And finally, we will print that count minus 1 as our final answer. Let's get to the implementation. So first, we start by taking the input for t test cases. Now, for each test case, we first take the input for the number of nodes, that is n. Now we create an array by the name n for storing the in degree. Note that I have created the vector of size n plus 1 because we will be using 1 based indexing for numbering the nodes. Now we will take the input for each edge. Now after taking the input for each edge and incrementing the in degree of the corresponding node, now we will count the total number of nodes having in degree exactly equals to 0. So let's create a variable for that by the name count, and for elements I equals to 1 to I equals to n, if my in degree is equals to 0, I increment my count, and finally I output my answer as count minus 1. And that's it. We are ready with our code. So let's submit this code on CodeChef ID and let's hope for a quick AC. Great, so our solution works. Regarding the complexity of this problem, we saw that we just took the input, and after taking the input, we iterated our array of this order of size n only once. So it is safe to say that the time complexity of this code is big O of n. So that's it for this one, guys. I hope you enjoyed the video. Make sure to like it. Also, to stay notified about more such content, make sure to subscribe and hit that bell icon. You can also stay updated through our Telegram channel. You can find the link in the description. Also, in case of any doubts or suggestions, feel free to comment below. If you have any more problems that you would want me to solve, make sure you mention them in the comments, and I'll see you in the next one. Bye.